filter's not as much of a notch filter, it's a little bit...
It's not really a filter at all, it's actually in the actual topology of the way that it switches. It doesn't generate as much noise in the first place.
Oh, okay.
So you haven't got as much that you have to filter out, is how they work. Yeah. So it's not practical to actually make a Class A amplifier that drives a big loudspeaker, so that's not.
And I guess you've also got the issue of where does that power go when it's not being used?
Well, yes, it's boiling. I mean, we'd need. It's just not. You just can't do it. Maybe it's not a possibility.
Hi there, it's Allan from Linn Klimax Glasgow. I'm delighted to welcome Roscoe, who is the design lead for the new Klimax Solo 800 amplifiers from Linn. We'll be chatting today a little bit about the background to the product and hopefully getting under the bonnet and learning some of the kind of tech spec. So without further ado, Nina, welcome.
Thank you.
No problem.
Good to be here.
Can I ask you a little bit about the kind of backstory to the amplifier? This is obviously quite a departure from Linn.
Yeah, it's quite a new venture.
Yeah, both in terms of scale and also performance. So where did it kind of come from?
So it started really because I think mainly particularly our American market, there have been a lot of questions about would we ever think about a much larger monoblock amplifier that's able to drive more, be spec'd into using 2 ohm loudspeakers, whereas previously we have history mostly of sticking to 4, 8 ohm kind of impedance levels, and could we increase the output power that we're able to deliver. So we kind of combined that with, we've of course had the Klimax Solo 500, which has been out for I think over 20 years now, which was kind of a bit of a descendant of the Linn Clout amplifier. And these have been fabulous amplifiers, very, very low distortion, very low noise, very clear, but relatively small, so we're looking 500 watts into 4 ohm load. Is really kind of the limit on a Solo 500 comfortable performance. I mean, it can drive lower impedances, but perhaps not quite so loud. So obviously during those 20 years, things have moved on in terms of electronic design, in terms of electronic components, in terms also even of what's possible in terms of the mechanical machining of metalwork. So we took the opportunity to see if we couldn't increase the performance quite dramatically at the same time. Really went back to the drawing board, looked at every single part of the power amplifier and worked on every single bit to particularly reduce distortion. The noise levels on a Solo 500 are already so low, quite frankly I think probably you'd be struggling to get much below that. So it's really about looking at distortion. So we have taken advantage of newer electronic topologies, but also the performance of some of the transistors that we've got is significantly higher than what was available when the Solo 500 was originally designed. We also wanted to make sure we weren't going to require any kind of forced air movement, so there's no fan in the Solo 800. So a lot of it has also been about how do we manage removing the heat from such a big amplifier. So when you're trying to, we're aiming for 800 watts into 4 ohms and something much more significant into a 2 ohm load. So the way that we have designed this, we have these quite tall fins on the side here, and because they're sitting vertically and the boards are sitting either side in here, and it's particularly the amplifier side that generates a lot of heat in a linear power supply, a linear power amplifier, sorry. So we have all the big output devices are sort of along the bottom here, and they deliver heat into this heat sink, and then natural convection, because obviously hot air rises. You get a really nice air movement up here, which is obviously totally silent, but it actually removes an awful lot of heat from the amplifier. And similarly, actually inside there are vents underneath in the base plate, and that feeds into this as a vent all the way around the outside of the lid. And we also get a lot of air movement actually through the middle of the product, and then it runs past other devices, the driver devices that can't be strapped to the heatsink quite so easily, removes a lot of heat from them, cools a transformer in the power supply board as well. And so we actually find that it runs really lovely and cool.
Great. Okay.
And just by good arrangement of where things have been placed on the metalwork. And we spent some time just making sure we've got these fins are just the right height, really. They're the right height to remove the heat at the power level that we're operating. So if they were a bit smaller, we'd be running, we would feel it would be a bit too hot. I mean, it would probably be okay, but that reduces long-term reliability. And also, I think at Linn, we're not keen on having the outside so hot that, you can't touch it comfortably. So it gets warm, but never sort of, it's never going to burn you or hurt you. So that's, but not so high that it's excessively large for no reason. It's just the right size.
Just the right size, perfect.
Just the right size,
Good.
exactly.
Excellent. So get under the bonnet of the amplifier. Obviously, Linn have used switch mode power supplies for many years in lots of products, which is, well, a tad controversial, shall we say?
Yeah.
What are the pros and cons? So what are the pros and cons of a switch mode power supply over a traditional kind of linear transformer-based power supply?
Yeah. So a linear power supply is depending on a transformer, a really big transformer. So that is you're not doing any switching, you're not generating any switching noise, and that's really the crux of why a lot of people don't like the switching power supply. Our feeling is, though, what you're then doing, if you've got a linear power supply, is you're taking 50 hertz or 60 hertz, depending on where you are in the world. You are then, that's what frequency the transformer is working at. We then have to put a whole pile of filtering on the output to try and remove all that mains voltage variation. In the best will in the world, you're never getting rid of all of it, and unless you've got the most amazing, even with the most incredible filtering, you're still going to have some left. And that makes its way into the audio circuitry. And because it's right in the audio band, it cannot be filtered out. Anything that gets into, at that frequency, that gets into the actual power amplifier is getting to the output. And it's really hard to get rid of it. Whereas with a switching power supply, it's very practical, particularly in this day and age, to switch that power supply at a frequency that is way beyond the audio band, which is what we do. So there is switching noise obviously in the box. We do filter it out to a very low level, so even if you do look out at the higher frequencies where the switching frequency lies, it is quite small, but the point is there's no way on earth you're going to be able to hear it. You just cannot hear it. So we find that we get much cleaner performances. There's nothing then left down at 50, 100 hertz. So when you look at the spectrum of this amplifier, there's just no harmonics popping up anywhere around 50, 100, 150 hertz. They're really, really low. Obviously something gets, a bit gets into any electronics that you've got running, even just more through pickup, through the air, really, more than anything else. But we find it gives a much, much cleaner audio band.
I guess you've also got the issue with toroidals where you've got a big magnetic field, you've got a big transformer, therefore you've got a big electromagnetic field around.
It has a really big shield around the transformer, and so it's a really challenging game. So the other big advantage of the switch mode power supply is it's very controlled. So the transformer output voltage varies quite a bit. With any fluctuations in the mains, it's much less well separated from the audio circuitry. So the switch mode power supply,
and also temperature
just
variations
control
as well.
loops, just remove it all. So you've got a very, very well regulated output voltage.
Do you deal with anything on the other side? Do you deal with any noise going back into the mains that any other audio components can kind of deal with? That was always, I think, one of the kind of points of less well implemented switch modes.
So all of our utopic power supplies have a power factor correction stage, so they are and then a lot of filtering, so we're not injecting an awful lot of noise back into the mains. Yes, we are trying to be a good citizen on the mains, as you might put it, just to
So the Utopic's part of that. So obviously the Utopic's a comparatively new product, and it's now trickling down to some of the other amplifiers and also some of the active loudspeakers.
It's kind of a range of power supplies, really, Utopic.
So what's the principle of the Utopic? How does that differ from what was the previous generation dynamic?
Just on the level of a bit of, again, it's a bit like the power amplifier. We're taking advantage of newer topologies, particularly of switch mode power supply topologies. So we're using, they're all resonant switching converters, so it means that they aren't generating as much harmonic noise in the first place, because it's a softer switching. it's about trying to make sure that your topology is allowing voltages to drop back to close to zero before you actually switch the switches by using inductor capacitor kind of resonant circuit, so it allows a natural.
So the filter's not as much of a notch filter. It's a little bit.
It's not really a filter at all. It's actually in the actual topology of the way that it switches. It doesn't generate as much noise in the first place. So you haven't got as much that you have to filter out. Is how they work. Yeah. And they're much more efficient as well, which is another sort of side benefit of them.
So again, that's just all about driving noise down.
So it's about driving noise down, and another benefit is that it does keep the amount of heat inside the box down. And electronics, as you probably know, doesn't really like to get just too hot. It's not good for either performance. Performance starts to go off the boil the hotter all the electronics gets. So the performance of the devices starts to reduce. So it impacts the audio performance. So that really cool switch-mode power supply is not generating all sorts of heat, which is just adding to the power amplifier noise. So if you've got a linear power amplifier, we can't get round, that's actually the laws of physics that kind of dictate the amount of dissipation that you get on the heatsink. Although we do regulate the rails a bit to deal with that. But if we don't also generate it, if you've got a big linear transformer in there, a linear power supply, you're just adding a whole pile of heat into there that doesn't need to be there. So.
And I guess you're also, the temperature within the amplifier is fluctuating as well, depending on the use. So the values are changing, and that's causing stability issues, I guess, and consistency issues.
Yes,
absolutely. Okay, interesting. Okay, so other things to do with the amplifier? There's been some talk about sort of adaptive bias control.
So this is like
what's the principle of that?
Uses the adaptive bias control. So the idea of that is what we do is we essentially.
So what is a biasing current in an amplifier then? What does that do?
So a linear power amplifier has a kind of output stage, which is it's really big transistors essentially, and they're being controlled by a lower power kind of front end to the power amplifier. Power amplifier generally consists of 3 stages, so it's got a kind of input stage, a nice differential input stage that generates a nice linear output current. Then it's what's called the voltage amplifier stage. It takes that input current and generates a nice big voltage. But that's not a very high power thing. That then gets translated through it's like basically a unity gain output stage, and that then adds the power. So these big transistors, their bases are controlled by the voltage amplifier, but they take their current directly in from the high voltage rails. So they what happens is when you're in a positive part of the output voltage, when it's positive, the top devices are working. When you're negative, the lower devices are working. So your problem is what happens in the middle. So you've probably possibly heard of Class A, Class AB, Class B. So in a Class A amplifier, all the top and bottom devices are all on all the time. And you then don't have any sort of crossover in between these 2 points. But the problem with that is, in order for them to stay on all the time, you have to have so much current going through there that it's actually bigger than what you're delivering to the speaker. So that's a huge amount of current if you've got a high power output. So it's not practical to actually make a Class A amplifier that drives a big loudspeaker, so that's not. And
I guess you've also got the issue of where does that power go when it's not being used.
Yes, it's boiling. Absolutely. I mean, you would need. It's just not. You just can't do it. Really, it's not a possibility. So you have to be Class AB, which is what Class AB means is that for some of the power output, you've got you can allow the opposite side that's not working to turn off completely, and then you've got a Class B amplifier, you just switch straight round about 0 volts, you stretch straight from top to bottom, but that generates what's called crossover distortion, so you can never make that transition perfect. So a Class AB amplifier has a little bit of bias current coming through these output devices, so that what happens is when you get sort of close-ish to 0, then you've actually got the top and the bottom both running at the same time, and you get a much smoother transition. But the exact amount of crossover distortion that you get, there is an optimum bias current in there that gives you the very smoothest handover between the top and the bottom devices. And if you have more current, then it's not as smooth, and if you have less current, it's not as smooth. So we want to try and hit that kind of sweet spot, and that's what the adaptive bias control does. I mean, there are conventional ways of achieving that as well, which is what the Solo 500 has, and the Clout had before it. All these amplifiers did have an optimum bias current. but it
But
was
that was
controlled
something
in
that
an
was
analog
kind of
domain.
preset as well, wasn't
And
it?
it was preset, exactly. So as they all have a bit of temperature adjustment. You can make an analog circuit with a bit of temperature adjustment. You know, they do have that, but it's never quite as perfect. And as the devices age, that the voltage that you need to get your optimum current starts to drift a bit. And obviously as they get very warm, if it doesn't follow very well with the temperature, you might be drifting quite a bit away from it. So the adaptive bias control, we measure the current in the top and the bottom of the devices. We then digitise
So
that
that's
measurement.
measured in the input stages then of the amplifier?
No, on the output stage. You have to measure it in the actual output. You need to know what the actual output current is, because that's dependent on frequency and
the impedance of the loudspeaker.
So it's quite difficult to do it any other way apart from actually in the output. And if you're going to actually control it as well, we then have to, it's a closed loop thing, so you must know what the real current is. Right. So we measure it on the output stage. It then gets digitised, and there's an FPGA in there that does essentially a lot of signal processing. So we extract calculate what the actual bias current is, because obviously we have to remove all the signal information from that to extract the actual bias current. And then it goes through, a kind of integrator, essentially, a closed loop control system into a DAC, digital to analog converter, and then generates a voltage across the bases of the output devices. And then, because it's closed loop, it will just settle at perfect current. So it just will be like that forever. It won't do anything else. So.
Clever bit of kit. Yeah, indeed. Okay, so anything else kind of unique that you've developed if you compare?
A lot of the rest of it I wouldn't say is necessarily unique. It's more we use every single technique that we could find that was going to be suitable and tested. We tried a few different variations for some parts of the circuit. We tried a couple of different options for the output stage, and settled on a triple emitter, which gives a really low output impedance. We have 8 parallel output devices, which reduces the current that each device carries, obviously, by 1/8. So you see a lot less distortion coming from each output device in the first place. Those output devices are very low distortion devices as well. They've really, the current's incredibly flat with the voltage current relationship's very flat. So but then what else have we done?
There does seem to be quite a lot of just attention to detail in terms of the sort of presentation of it. When I was setting it up earlier, there's little rings that sit below, isolation rings that sit on the feet as well, which I thought was quite a nice. So obviously a little bit of mechanical isolation. As well.
I think it's the same feet that we have on the DS.
I think it is. It's on the Klimax DSM. It's similar,
and
it's the kind of 3. It's the 3 foot as well, so it gives you a little bit of stability. So it's the whole thing smacks of just attention to detail. Which is if you've had what every engineer wants. You've had the budget and the ability to be able to look at each individual part.
I mean, a lot of what's in the electronics actually, as it happens, it's not desperately expensive. The electronics, it's really just been a case of choosing the correct topology. It's just worth spending the time trying different things and reading. We did a lot of reading to see what would be the best bit for each single component of it. And then around it we also have, we should perhaps mention, there is an error correction loop around the whole thing. That's very high gain, that takes any residual distortion that is left in the output. It does then reduce it by quite a bit again. So,
great.
so excellent. Just every single bit.
That's been great, and we're looking forward to, I guess, some of the technology trickling down into some of the perhaps more affordable products.
Well, more affordable ones. I was going to say the 360 has as well. It's not really a more affordable product.
That's not really a more affordable product, but we're looking forward to seeing that as well. So that was great, Thank you very much for that. That was really informative.
Pleasure.
Hi there, it's Alan here from Linn Klimax Glasgow. Linn Klimax is Scotland's premier hi-fi and home cinema retailer and installer. The purpose of this channel is to give you a little bit of insight into some of the behind the scenes of the hi-fi industry. We're interviewing some techs, some salespeople, and we're trying to find out some really interesting information about some of the brands we know and love. If you think this is the kind of thing that might be of interest to you, please like and subscribe.